Okay, we'll now be studying about the composition of angular velocities and angular accelerations and see how they are useful in our understanding of this kinematics. So this is especially useful when you have, say, the motion of a body is described with another body to which it is connected. Typically this happens in a machine, and in those situations you have these relative velocities and uh, uh, relative angular velocities. So you want to give that a breakup. Now let's see how we can show that it's actually just simple addition. We have done a similar thing before, but not for angular velocities and acceleration. Let's see. So we will show the simple addition relation for of angular velocities okay, and that must be done using equation 1.50. so let me pull out that equation for you using 1.50, and 1.50, if you would recall, we have used it several times. Okay, so let omega 31, omega 32, omega 21 be the angular velocities of frame 3 with respect to frame 1. Okay, that I think this is subscript already tells that. Similarly, omega 32 will be the relative velocity of frame 3 with respect to frame 2 and frame 2 with respect to frame 1, okay, respectively. So let me just show that with a simple diagram. You have this frame 1, you have this frame 2, and then you have this frame 3. Okay, now this particular 2 is rotating with respect to 1 by omega to 1. Say this is the vector which is there, and this has a omega 3 with respect to 2, this has a omega 3 with respect to 1. Okay, now you can write about this vector A at this given time t as using this 1.50 which you have over here as A dot 1 equal to A dot 3 plus omega of 3 with respect to 1 cross A. This can also be written, so F is automatically the first frame, okay, and this third is the M frame, but you can also write this in terms of the second frame. That would be A dot with respect to 2 plus omega of 2 with respect to 1 cross A. Okay, both of these hold. And if you want to write omega 2 with respect to, so let me just write out this first. So we want to write this particular thing as A of You want to use 1.50 again on this, and that would make this as in terms of the third frame. So A dot with respect to 3 plus omega 3 2 cross A cross plus omega 2 of 1 cross A. Okay. Three plus, okay, and then I would write omega 3, sorry, omega 3 by 2 plus omega 2 by 1 cross A. Okay, and this would be valid for all vectors A. Clearly I didn't write that specifically. Now this implies that omega 3 by 1 is equal to omega 3 by 2 plus omega 2 by 1. How do I know that? You have to compare this equation with this equation. Okay, so when you do that, you will realize that this particular term is the same as this particular term, and hence we are able to write it. Okay, so that is omega of 3 by 1 is equal to omega of 2 by 1 plus omega of 3 by 2. Okay, this is equation 1.73. So this is the so-called simple addition, okay, which one can see over here. Okay, now we want to do a similar thing for the angular acceleration. So let me start off with that. Omega 3 by 1, the entire thing is dot in the one frame. This will be omega 2 by 1, this entire thing dot in the one frame. Okay, we are just differentiating this, okay, equation, plus omega 3 by 2, this entire thing dotted with time in the first frame. Okay, so this has come by differentiating this with respect to time in the first frame, okay, with respect to the first frame. Now we can write this separately as omega dot 2 by 1. This particular term can just be written like this, and omega 3 by 2 dot in the first frame, can we now use equation this 1.50. Okay, so we'll be using it in the, so M becomes the second frame over here, so F is the first frame, so this we want to write in the second frame. That would be omega of 3 by 2 dot in the second frame plus omega of 2 by 1 cross omega 3 by 2. Okay, now so this is by using 1.50 again. 1.50 seems to be the most important equation as of yet. Okay, now omega 3 by 1, this particular term which you have, is equal to omega dot 2 by 1 plus omega dot 3 by 2 plus omega 2 by 1 cross omega 3 by 2. Okay. Now in your text you have a warning. The warning is that in general, see, look at this equation, okay, over here, omega 3 by 1, and now look at omega 3 by 1 dot, okay. So omega 3 by 1 seems to follow this simple relation, but here you have these additional terms, okay. So that's why we say that omega dot 3 by 1 is not equal to omega 2 by 1 plus omega dot 3 by 2, okay, because of this additional term. So simple addition rule is not valid as it was valid over here, okay. Valid here, okay. Now if frame 3 is the same as frame 1, so clearly omega 3 by 1 would all be 0, and then equation 1.73, which you can see now, this is 1.74, 1.73 will become omega of 2 by 1 is equal to minus of omega omega of 1 by 2 is equal to omega of 2 by 1, okay, when 3 is equal to 1. So omega 3 by 1 will be omega 1 by 1, that is 0, omega 2 by 1 will remain what it is, and omega 3 by 2 will become omega of 1 by 2. So that is what you have. And similarly 1.74, equation 1.74 will become omega dot 1 by 2 is equal to minus of omega dot 2 by 1, okay, sorry, 2 by 1, okay. Okay, so this particular term would be 0, okay, this particular term would be 1 by 2, and this particular term would be 1 by 2 again. So 1 by 2 cross 1 by 2 would be 0, hence you have this, okay. This is equation 1.74. You could have also taken a derivative with respect to time over here, but we are not doing that just because we have derived a more general equation. So it's always safer to use equations like this, okay. So I'll just remove that over here, okay. So this is 1.75. So if you have to write these statements in words, you would say the angular velocity and angular velocity and angular acceleration of frame 1 with respect to frame 2 are equal in magnitude and opposite in direction. to the angular velocity and acceleration of frame 2 with respect to frame 1. Okay, so because that opposite, you can see opposite direction because of the minus sign. So you will see that if you have interconnected bodies like this, okay, 1, 2 and 3, in any of the situations or problems which you are dealing with, then if the final answer is sought in for this one frame, you normally call it the F frame. Okay, and then each of the bodies are like, this is body 1, this is body 2, body 3, body 4, so it can just keep on going. A usual machine will have lots of interconnected bodies which will have kinematics, motions of one relative to the other and the other relative to the other one, and so on. Okay, so knowing that, you would use these equations which we have just derived, 1.73, 1.74, 1.75, and write the terms as omega 2 with respect to f is equal to omega 1 with respect to f plus omega of 2 with respect to 1. Okay, this is the simple addition, and clearly the simple addition doesn't work when it comes to angular acceleration. So I'll show it to you how it's written. Well, it's automatically over here, so let me keep that. It's over here. Okay, it's of 2 with respect to f dot is equal to omega of 1 with respect to f plus omega of 2 with respect to 1 dot plus omega of 1 with respect to f cross omega of 2 with respect to 1. Omega of 3 with respect to f is equal to omega of 2 with respect to f plus omega of 3 with respect to 2, and you would have omega dot 3 by f is equal to omega of 2 with respect to f dot plus omega of 2 with respect to f cross omega of 3 with respect to 2. Okay, now for omega 3, we can write as omega 1 plus omega of 2 by 1 plus omega 3 by 2. This you can write from these two equations. Okay, so f is clearly dropped now, so you can write over here, these two will give you this, and similarly omega dot 3, okay, you can write using these two equations. I'll just show over here. That would be equal to omega 1 plus omega dot 1 plus omega dot 2 with respect to 1 plus omega of 1 cross omega of 2 by 1 plus omega dot 3 by 2 plus omega 2 cross omega 3 by 2. Okay, this is coming from over here, where this 2 dot f is taken from over here, and that is what you have. Okay, so f subscript is dropped. and this can be written as omega dot 1 plus omega dot 2 of 1 plus omega cross omega 2 of 1 plus omega dot 3 of 2 plus, and then this particular term omega 2 can be written as omega 1 plus omega 2 by 1. How? This is coming from over here, this equation. Okay, so that's what you have, and then this is cross omega 3 by 2. So f has been dropped, it's given f has been dropped. Just for convenience, okay, not that it's not important. So it is needless to say that something like omega 1 over here is the angular velocity with respect to frame f. Okay, similarly this is angular velocity of 2 with respect to frame f. If there are three bodies like f1 and 2 and 3, okay, sorry, then this term omega 1 is the angular velocity of 1 with respect to f, and omega 2 is the angular velocity of 2 not with respect to 1 but with respect to f. Okay, and similarly this particular thing, okay, sorry, this is omega 1, and this thing is also the angular velocity of 2 with respect to 2 with respect to f. So this entire thing also with respect to f. Okay, so you should be able to, you don't have to, but you should be able to, let me write in red. Should be able to extend it to n interconnected bodies. So the topic we are now about to discuss is rolling without slip, and this is very important in terms of the practical applications, like all of them, but this is actually very important, and its theory is very directly applicable in many situations. Okay, and so let's see how we deal with this. So let me draw a couple of figures first. Okay, so pi, okay, and then okay, so let's discuss this. So you let the material point P1. Now by this time, if you have forgotten about the material point and how it was defined in terms of the continuum hypothesis, this is a good time to actually pause the video and go back and learn about this concept of material point. Okay, so let the material point P1 and P2 of bodies 1 and 2 be in contact at time t1. Okay, so we will say that the components of their velocities, it will obviously have a normal and a tangential component. So let's see the components of their velocity along the normal n to the tangent plane pi. You can see the tangent plane pi in the figure. Of the surfaces at P1 and P2 are equal. As otherwise the bodies will separate. Or penetrate each other. So we don't allow penetration because both of the bodies are rigid, okay, and they can't be separate because we are telling that they are at contact, okay. Hence the velocity, the normal component and the normal component of the velocity along the normal n to the tangent plane pi of the surfaces at P1, P2 are equal, okay. If they are not equal, then it will either separate out or it will penetrate. Okay, hence the relative normal velocity, so called, is 0. That's the point. Now if body 1 rolls or slides on body 2, in general the components of AP1 and AP2 along n differ. Okay. So this will be because different points make contact at different instants. So right now you can see this as the point of contact, and if they were just sitting here like this, their normal velocities would be the same, so there would be no relative normal velocity. But if there is a rolling or a sliding of body 1 on 2, then in general the acceleration along these two directions will be different. Okay, because I mean you have different points making contact at different instance. So at this time these points are in contact, but at some other point some other points will be in contact. Okay, so that's the reason why the accelerations at along n have to be different. Now we want to consider this no slip situation. Okay, so no slip between P1 and P2. Remember, P1 and P2 are the material points in the tangent plane pi their velocity components in this plane must be equal. This implies that this velocity of P1, P2 in the F frame at given time must be equal to 0, or velocity of P1 is in the F frame at this time is equal to the velocity of P2 in the F frame at the same time for all frames F. Okay, now what does that anytime instance shows? It shows that it's not in contact. So the relative velocity is 0 now, and relative velocity is 0 forever practically. Okay, this is for all times, and that's where the acceleration term which we have just read over here also plays a role. So both of them, these quantities would be 0. So let's consider three conditions. I mean, this will be more clear if we consider three possibilities. So there are three possibilities. So one is that slip at T1 if Vp1 by F T1 is equal to not equal to Vp2 of F T1. Okay, so clearly there will be a slip if the relative velocity is not 0, and hence that means that velocity of P1 at this time, it's always at this given time T1, okay, is equal to the velocity, is not equal to the velocity of P2 at the same time. You say that there is no slip at the same time T1 if velocity of P1 with respect to F T1 is equal to velocity of P2 F of T2, okay, at T1, and this is important, not an option, okay. Subsequently, the velocity of P1 plus of F at T1 plus is equal to velocity of P2 plus of T2 plus, sorry, T1, this is not T2, sorry, this is T1 plus 4 corresponding different material points. P1 plus P2 plus in contact at t1 plus. Okay, so it means that at this current time the relative velocities are 0, and it means that when the time is slightly changed, okay, so t1 plus is that next instant of time or time ahead of t1, at that instant the relative velocity between the contacting points at that time, which is v, this p1 plus and p2 plus, is also the same. Okay, so p1 p2 was in contact at t1, relative velocity 0. p1 plus and p2 plus is contacting at t1 plus and the relative velocity is still 0. Okay, this is called a no slip condition. Both of them have to be satisfied, not just at that instant t1. Okay, now this does not automatically imply that a p1 by f of t1 is equal to a p2 of f at t1. Okay, and you should answer why in the sense you should be able to go back to the discussions which we have had about relative velocities and acceleration and tell why this does not automatically imply this, okay, in general. Okay, because t1 over here, t1 plus over here is not the referring to the contacting between p1 and p2. Okay, that's the reason. So you should be able to answer this perfectly. So t1 plus, if you remember, is the time at which p1 plus and p2 plus are in contact. So you cannot use that over here for p1 and p2. Okay, now we have this situation of a impending step, the last condition. Does not imply, I'll just put it, okay, at t1 if v of p1 of f of t1 is equal to v of p2 f at t1 at t1, but this equality does not hold for the corresponding contacting points p1 plus and p2 plus in contact at t1 plus. That is, the velocity of p1 plus with frame f at time t1 plus is not equal to the velocity of p2 plus at f with respect to t1 plus. Okay, for all reference frame. Let me call it any reference frame. So all this is with respect to any one reference frame you want. Okay, so if you look at equation 1.59 over here, that tells us something. So 1.59 is the velocity of a material point P in the F frame is equal to the velocity of a material point A in the M frame, okay, plus, so A is lying in the M frame, but this velocity is observed using the F frame. If please go back and check equation 1.59, and this is RPA plus VP of M. Okay, now using this we can say that if velocities, you can write it for points P1 and P2 separately in the same exact equation 1.59. okay, you can write two equations, one for P1, one for P2. So if velocities are equal or unequal in frame F, then the same holds for other frames M with omega M with respect to F, okay, as R P1 P2 is equal to 0 at T1. okay, so if P is a point and A is a point on M, okay, so you can say that the velocity of P1 in F frame is the velocity of A in F frame plus omega cross R P1 A plus velocity of P1 in the M frame. Similarly, you can write the P2, contacting point P2, velocity of F plus omega cross R P2 A plus velocity of P2 by M. Now if P1, if V P1 by F is equal to V P2 by F, then you will have VA by F is equal, sorry, I should write it as omega cross R P1 of A minus omega of R P2 by A is equal to V P1 by M minus V P2 by M. This would mean that omega cross R of P1 P2, okay, since R P1 minus R P2 is equal to, with respect to any point, is equal to R P1, okay, P1 P2. This is something which we studied at the very start, okay, and the same can be applied, and this is equal to V P1 M minus V P2 of M. Now this number would be 0 at T1 since they are in contact, okay, so R P1 P2 will be equal to 0, and this would imply that the velocities are actually equal to, in the M frame, are equal, okay, so that is why we are able to say that the velocities are equal or unequal in frame F, then the same holds for other frames M. So velocity was assumed to be equal in F frame, and we came out with this equal velocities in the M frame as well, okay. So this is frame independent, this relationship, and that's why we always have this F for any frame, okay. A similar thing of inequality will apply. If this is not equal over here, then these velocities will also not be equal. So let me do that by a red one. If this is not equal, then this will also not come out to be equal. Okay. So if a situation, I mean, we had actually drawn this diagram over here. Over here you have this cylinder rolling over here. You have this cylinder rolling over this circular section. Okay, this is fixed clearly, and this is moving. So we want to consider this situation in which this body 2 is fixed or is at rest and body 1 is moving. So let's do that in detail now. If body 2 is at rest, then above definitions and for no slip, velocity of P1 at T1 is equal to 0. If body 2 is at rest, then obviously the velocity of P2 at this time is equal to 0 in the above definitions, and then for no slip, velocity of P1 has to be the same as velocity of P2, which is equal to 0. Okay, so this implies that if 1 is a rigid body, then P1 is an instantaneous axis of rotation. P1 is on its instantaneous axis of rotation, and all additional points of contact of body 1 on 2 must lie on this axis. Lie on this axis parallel to omega 1. So if 1 is a rigid body, then P1 is on its instantaneous axis rotation, and all additional points of contact of body 1 on 2 must lie on this axis parallel to omega 1. Okay, so that would look like, let me show that. Okay, and okay, pardon the sketches, but I think they are conveying what I want to convey. So Q and P are at this given instant T1, and body 2 is this which contains the point Q. It is at rest, and hence the velocity of this particular point is also p is also equal to 0 at this time for no slip. Okay, now at the next some other time, this is q dash, and this is p1 sorry, p dash. So this is the instantaneous is this lying on its instantaneous axis of rotation. So the axis actually goes into the screen through this contact point. Okay, and any additional point which you have must lie on this axis parallel to omega 1. So this point of contact will be different, and all of them will be lying on respective axis of contacts, which will all be parallel to each other, which is in the direction of omega 1. So at this point you can go back and check what the instantaneous center and instantaneous axis of rotation was. Okay, the point is that when you have this, then the velocity of this particular point is 0, which is the case over here. Okay, now let's have an equivalent definition. This is for obviously rolling without slipping, is that the curves on the surfaces in rolling contact be tangential the arcs traversed on them between successive points be of equal length L, be of equal length. Okay, for rolling without slip, QQ dash is equal to PP dash. Okay, let's try to understand the meaning of this. So at some instant you have P and Q in contact, and then there is rolling without slipping, and then the other instance P dash and Q dash are in contact, and this P which I have shown in blue color is where this original point of contact was. Okay, this black P which you have has become a blue P because now that point has moved behind. Okay, so that is what I mean by this. Now we are saying that QQ dash is the same as PP dash, meaning this particular distance is the same as this particular distance. The curves on the surfaces in rolling contact be tangential, and the arcs traveled on them between successive points of contact be of equal length. So that is why this QQ dash is the arc and PP dash is the arc, and they are the same. So this is an equivalent definition of rolling without slipping, because if there was any slipping, there would be a distance between these two quantities. Okay, so that is what is used as a alternative definition of rolling without slipping. Okay, so when you have, say, the wheel moving on a road, or a roller bearing on the bearing race, or a billiards ball on a table, then that is all rolling without slipping. Okay, there is no slip at all points of contact. So this is something very important and many a times desirable. Okay. So let's try to see how this definition, this equivalent definition and the earlier definition are actually the same. Okay. So let me just first draw a diagram. So you have okay, so this is this P1, same as P2 contacting. Okay, so let's see one by one as we discuss this. So this is 2, this is 1. So relative to frame of body with plane of motion frame of body 2 omega 2 is equal to 0, let omega 1 is equal to omega 1 k hat. Okay, so this is rotating by omega 1 and this is rotating by omega 2. The bounding curve C1 of body 1 rolls over the bounding curve C2 of body 2. So this is the bounding curve C1 which rolls over the bounding curve C2. Okay. At the given instant, a material point P1 of body 1 makes contact with the material point P2 of body 2, that is shown over here. Consider a common slider which slides on C1 and C2. So if you have a slider which slides on C1 and C2, so this blue is the slider, okay, and which at the given instant is coincident with P1 and P2. Okay, so we can write that, I'll write in blue itself, P1 of S is the same as P2 of S is equal to 0. Okay, so at this instant it is coincident. At this instant is coincident with P1 and P2, and that makes sense, right? Because the relative position of P1 and P2, P1 vector P1 P2 will be 0. Okay, based on this, so it's okay, fine. So S, actually I should show you, I mean I have shown an enlarged view, but Actually it is this point. Okay, it's just shown in enlarged view. Now C1, C2 are the trajectories of S relative to bodies 1 and 2 with path coordinates. So this is where the path coordinates are coming in. So let me just write that C1 and C2 are the coordinates of S, coordinates of coordinates of trajectories, I think is a better word here. I mean the coordinate is S, so that's not an issue. Trajectories of S relative to bodies 1 and 2 with path coordinates S1 and S2. Okay, we find expressions for, you must have got an idea about path coordinate when we were discussing this. Okay, when we were discussing the arc q1 q dash and pp p dash. Okay, so that must have been a hint. If not, I think we are anyways laying it out explicitly over here. So we want to find v of p1 p2 and a of p1 p2. So let's write the velocity of the slider, that is velocity of p1 plus omega 1 cross p1s plus velocity of slider in frame 1 with respect to body 1. Okay, so do you recall this expression? You must be able to now pause the video and go back from where this particular expression has been taken. Check that derivation and only then come back. Okay, so this is Vp2 plus Vs with respect to 2. Okay, sorry. And the reason this is there because omega 2 is actually equal to 0. Okay, that's why, so you have written the velocity of slider in terms of the p1 and p2. Okay, so now this implies that the velocity of p1 p2 is equal to the velocity of p1 minus velocity of p2, and this, if you can use this expression over here, this will be equal to vs2 minus vs1. Okay, and this is equal to s2 dot minus s1 dot in the tangential direction. So let me show that direction over here. I'll show in blue. This is the ET hat and this is the EN hat. Okay, let's call this as 3. EN1, this can be called as EN2. Okay, so velocity of p1 is written as velocity of s with respect to 2 minus velocity of s with respect to 1, and this is equal to s2 dot minus s1 dot. Okay, now okay, So this is in terms of path coordinates. Now let's write the acceleration of s similarly. That is, again, you should be able to go back to the expressions which are relevant. It will have both the centripetal and the Coriolis terms. First we will write in terms of AP1 plus omega dot 1 cross P1s plus omega 1 plus 2 omega 1 cross Vs1 okay. Same can be written in terms of P2. A lot of the terms will be 0. Okay, so omega 2 would be 0, so all of this goes away and you will just have acceleration of s with respect to 2. Okay. Now, do you see a reason why when I used this and this, I missed out the omega 1 term, omega 1 cross P1s, okay, coming from here to here. The reason I missed out, not because omega 1 was 0, but it was P1s was equal to 0. Remember this thing. And similarly P2s will also be 0. So even though omega 2 is 0, okay, omega 2 is 0 over here, that makes it easy, but P2s in this expression would also be 0, hence all these terms would be 0. It will be 0 plus 0 plus 0 for omega 2. Now again I can write a P1 P2 using this, so that would be a P1 P2, sorry, a P1 P2 P1 minus a P2, okay, and this, using these two expressions, I can write it as a S2 minus a S1, or this is equal to, sorry, minus, oh sorry, omega 1 is not 0, right? So this would be 2 omega 1 cross Vs1. Okay, omega 2 is 0, not omega 1. So this should have this term minus of 2 times of omega 1 S1 dot k hat cross Et. So this quantity omega 1 vector is actually equal to omega 1 k1 hat, and Vs1 is equal to S1 dot Et hat. Okay, so this is equal to omega 1. Let me write in a separate color over here. This quantity is equal to omega 1 k hat. This quantity is equal to S dot Et hat, and when you do their cross product you get what is written in black. Okay, this is equal to now S2 double dot minus S1 double dot Et hat. Okay, because this is equal to S2 double dot Et hat, this is equal to S1 double dot Et hat, minus of S1 dot whole square by rho 1 plus S2 dot. Do you recall how we are writing this? The normal term, okay, and then to omega 1 s1 dot k1 into et hat. So the acceleration, so there will also be a normal term over here, right? En and En. Okay. So both of them have this normal components as well. So the tangential components are over here and the normal ones are over here. Now you can see that in this diagram, En1 is equal to minus of En2. Okay, that has played a role over there. That's why you have a positive sign over here. Okay, and you have written everything in terms of En1. The tangential direction for both of them are same, Et, but the normal ones are En1 or En2. So since En1 is minus of En2, that's why you have a positive sign over here. Okay, so this is equation 2. I should perhaps write equation 1 as well. This is equation 1. Okay. So if you want to write the tangential component of A P1 P2, then it would be A P1 P2 dot ET. This would be S2 double dot minus S1 double dot. This is 3. So this is the component in the tangent plane. We called it the pi plane earlier. Now think of 3 cases again at the instant t is equal to t1 plus t1. Okay, so at the time t equal to t1, consider the following 3 cases. There is a slip, so we have slip if Vp1 P2 at this time is equal to 0, not equal to 0, and equation 1 then implies, this is equation 1, okay, 1 then implies that S2 dot of T1 is not equal to S1 dot of T1. Okay, or ds2 is not equal to ds1. A small increment in s2 is not equal to a small increment in s1 at t1. Okay, so there is slip definitely. There is no slip if the velocity of p1 p2 at the given time t1, should write, since t is equal to t1, it is equal to 0, and t equal to t1 plus, okay, you have s2 dot of t1 is equal to s1 dot at t1, and ds2 is equal to ds1 at t1, and S2 double dot at T1 is equal to S1 double dot at T1. Okay. Okay, so since this is true, okay, this implies this is there, and this also implies that the acceleration is also equal at this given time. Okay, so for no slip, if you look at equation 3, okay, then that would mean that this A P1 P2 has no component along the tangential direction, or no component in the tangential plane, but it may have, look at equation 2, it will not have a contact in this because this value is 0, but this particular quantity is not 0, so it may have a contact in the normal uh, normal to it. So let me write that in words. By equation 2 and 3 above, A P1 P2 has no component in the tangential plane of contact, but can have this is sorry equal to, not equal to 0. Okay, otherwise you could have said the same over here, so this is not equal to 0. Okay, but it can have, I've just revised it over here, so ds2 is not equal to ds1 in this case, there's a slip. Okay, contact, but can have a component normal to it. Okay, now let's consider the third case, impending slip. If Vp1 P2 is equal to 0, sorry, I should write it at the time, is equal to 0, but is just violated at t equal to t1 plus. I don't want to use the word just, somehow I'm not convinced. So the relative velocity is 0 at this time, but at the very next instant it is not true. Okay, this implies, according to equation 1, you have s2 dot at t1 is equal to s1 dot at t1, but just violated, again not using just, but violated at t equal to t1 plus. Okay, this implies that the modulus of s2 dot t1 plus minus s1 dot t1 plus is not equal to 0. This implies that s2 double dot t1 is not equal to s2 double dot of s1 double dot of, sorry, at t1. Okay, so the velocity is 0, but the acceleration is not 0. Okay, so A P1 P2 has a non-zero component in tangential plane. Contact. Okay, so if you have to look at equation 3 to see this. So S2 double dot is not the same as S1 double dot, and hence this will be a non-zero quantity, and hence they are saying that acceleration of P1 P2 A P1 P2 has a non-zero component in the tangential plane of contact. So this shows the equivalence of two definitions of rolling without slip. So the first definition you had seen that about the three cases, and the second was about this one. Okay, so this could have only been done with respect to path coordinates. Okay, so since you have this situation that ds1 is equal to ds2, so if you integrate both of them over the path, you will get the same quantity. Okay, so that's where this is coming up from for rolling without slipping, which is case 2. So you should be able to verify this also. I mean, I have already done this, but you should do that last step. Okay, which part? Q dash is equal to P dash. These arcs are the same, so you have to use the path coordinates, and case 2, okay, which is rolling without slipping. Okay, so this finishes the case of rolling without slipping. We can take up perhaps the last topic of this discussion on kinematics, which is called gear, belt and chain drives. It is more related towards the application of the theory which we have just done, so I will just briefly go through it, okay, about this no slip condition. Okay. So there is I mean, just as a fact we are stating this. You will have to look up the applications of this through some videos on the internet or elsewhere, that there is no slip condition at belt. Now this can be a conveyor belt like this, okay, which say carries a parcel from this end to this end if there's a rotation. So this is the belt. Okay, this now moves because of this rotation of this. The belt will transfer this box to this end. Okay, then you have similar chain drives. You can also have a no slip. How do we have to look at a bicycle? Bicycle motion, or even a standing one. Okay, you just have to look at the chain of the bicycle and see how there is no slip condition over there. And the last is the pitch circles of gears. Look up some video or animation which show the motion of gears. Okay, I think 2 of them are okay. You don't get confused with a lot of them. And you can, even if you have a bicycle which has gears, perhaps you can try to see, but it will be harder to look at it over here. But you should be able to see this and move ahead only once you have seen and understood why there is a no slip condition. So this is a homework for you. This is something which you should look up. So I will just take up one simple situation. If you have this, I'm looking at the gear from the front, okay. Then this is meshed with the other gear over here. Okay, so it has a number of tooth, and that's how the power ratios are decided. So I think you should learn about this anyways. This is rotating by omega 1, this is rotating by omega 2, the ratio is R1, the radius is R2, okay, and this is okay. Now the omega which you see over here, omega 1 and 2, is the angular velocity with respect to ground. Okay, so this is the point of contact over here, okay, and this is in so-called no slip condition. So omega, so the velocity of over here is omega 1 r1, clearly the tangential component, and that has to be equal to minus of omega 2 r2. Why is there a minus sign? Is something which you should answer, and that is only true for this situation. Okay, I think the answer will come out once you exactly understand how the motion is taking place. Okay. And let's take up one more situation. Let's take up something like this, slightly inclined. Okay, becomes slightly ugly. So let's say that this is let's have a meshing like this. Okay, so the two gears are meshed like this in a certain situation, and so this is R4, this is R3, okay, then you have omega 3 and the direction is shown to you, and then you have omega 1, the direction is shown to you. Okay, in this situation, for no slip over here, you should have omega 3 R3 is equal to omega 4 R4. Okay, so why is there a plus sign over here and a minus sign over here? It should just come out if you understand the relative velocities better, and the answer is all discussed above. Okay, So don't use some loose methods to come to this conclusion. So normally when you go into detail to study about this gears, you will say that the radius can somehow be related to the number of teeth and so on. We are not going that far, okay, but you should just be aware of this situation, okay, fine. So this is where we can end our discussion on kinematics, unless there is some other important issue which must be discussed. So thank you.